Hi folks, welcome to this multi-part lecture. I hope you're doing well. The topic of this series, if we want to call it that, is Bode plotting, and in particular the focus is on the straight line method. This first session is going to be just a brief introduction and then talk about doing the Bode plot for constant gains. Later sections will deal with poles and zeros, be they simple poles or simple zeros, quadratic poles and zeros, things like that. So I want to kick things off with just a little bit of reminder material. If you recall, we have our transfer function h of s equals n of s over d of s. Now n and d are both polynomials in s, and our handout discusses that in pretty significant detail. And we can compute the frequency response by evaluating h of s for s equal j omega over some useful range of omega. So some range of omega, where omega is our frequency variable in radians per second. All right, so generally h of s is complex valued. So at any particular frequency, so at some omega equals omega naught, then h of j omega naught would have some magnitude, we'll just call it m, and an angle, we'll call it theta. And that's just a complex number at that particular frequency point. If we evaluate it at some other frequency point, we'll get a different complex number. And the frequency response is basically comprised of computing the magnitude and phase, or the complex value, over a useful range of frequencies, as mentioned before. So looking at the analytical representation that we might have for the transfer function h of s, it's not very easy all the time to determine what the frequency response would look like or what its characteristics are. So we usually want to find some way to plot that. And of course, plotting the complex values can also be difficult, but we do have some structured methods to do that. So one of them is called a Bode plot. And if you recall, the Bode plot, we have the magnitude plot and we have the phase plot. So we plot the magnitude and the phases separately, both as functions of frequency. So we have the frequency axis here, and then for the magnitude we'd have the amplitude, or the unitless amplitude or unitless magnitude, or the magnitude in dB, and for the phase we would have the angle in degrees. So again, though, that can be a little bit difficult to do if you're just looking at the analytical representation of the transfer function. So we want to develop some tools here that will allow us to do that, not quite by inspection, but at least it'll allow us to build out some reasonable approximation of the plot so that we can do some sort of analysis or design work. To continue a little bit with our introduction, we're going to again write our rational polynomial transfer function. So we're going to write h of s equals, and I'll just generically write b sub m s to the m plus b sub m minus 1 s to the m minus 1 plus, and we count down in our variable there, down to b1 s plus b0. All right, so all of these b sub m terms, or b sub I terms, are coefficients for the numerator polynomial. And then we're going to divide that by something that looks like a sub, oops, I want to use n here because n and m don't have to be the same. So a sub n s to the n plus a sub n minus 1 s to the n minus 1. And we're going to let that run all the way down to a1s plus a0. So again, that is a rational polynomial transfer function. The variable is s, and we have all these coefficients, the a's in the denominator and the b's in the numerator. And why it's organized like that is basically convention. For our case, all of the a's and the b's will be real valued. Now it turns out that we can factor this polynomial. Now, it might be hard to do, but we can factor the numerator and denominator polynomials into a form that looks something like this. H of s equals some constant value k, that's just a number, a real number, and then it would be in the numerator, we would have s minus z1 times s minus z2 all the way up to s minus z sub m, because we have m, it's a degree m polynomial in the numerator. That means it has m roots, and we call those roots zeros because they're in the numerator. Because remember, if we plug in a value in the numerator for s such that the numerator polynomial evaluates to 0, that is a root of that polynomial. And a degree m, as in Mary, polynomial has m roots, and we call those zeros in this case. The denominator works the same way. We would factor it as s minus p1. We'll call the p1 the poles, p sub I the poles, s minus p2, and so on until we get to s minus p sub n. So that is another way to represent the same polynomial. Now, again, as I mentioned before, this factoring operation can be quite difficult. Matter of fact, once you get above about third degree polynomials, doing this factoring by hand, other than for certain special cases, can be practically impossible, and you have to resort to numerical methods. However, that doesn't stop us from having our discussion here, because we're going to talk about most of these things, at least initially, in the somewhat abstract sense, and talk about how these various poles and zeros and this constant gain k lend themselves to helping us compute the frequency response plot, or Bode plot, for the given transfer function. Now, something important to understand here in terms of these factorizations is the z sub I terms in the numerator. So these terms here do not have to be real valued, nor do the p sub I terms. That means the poles and zeros themselves are not necessarily real valued, even if the coefficients, the a's and b's, are real valued. But what will happen is any complex pole or complex zero. So let's suppose that z2 is a complex pole or a complex zero for our transfer function. Then there has to be a corresponding zero that is the complex conjugate of z2. So again, so what happens is all complex roots of polynomials with real valued coefficients must occur in complex conjugate pairs. Polynomials with real valued coefficients will have roots that are either real valued or they will appear as complex conjugate pairs. And you can obviously have combinations of both. So we have 7 basic types of elements in our factored polynomials. Okay, so these are 1, a constant gain, which we'll just call k. That's going to be the topic of the rest of this particular portion of our lecture series. 2, we can have what's called a 0 at the origin, and this looks sort of like an S term. We can have a pole at the origin, and that's going to look like a 1 over S term. We can also have what's called a simple zero, or sometimes they call that a real zero, and that's going to look something like an S plus A term. Okay, and we can also have a simple pole. You probably see, let's carry this line out a little further just to make it easier to draw. 1 over S plus A. It's going to look something like that. And then finally, we have quadratic zeros and poles. So the sixth one would be a quadratic. Sometimes people call them complex conjugate pairs or complex poles. Um, we're going to say a quadratic, or zeros and poles. So we'll say a quadratic zero. And that's going to look something like AS squared plus BS plus C. Now we're going to cast it in a little bit different form, but don't worry about that right now. And then our seventh one is a quadratic pole. And again, that's going to look like 1 over AS squared plus BS plus C. All right, so our journey through the next couple of lectures is going to be to deal with how to make frequency domain plots of all of these components of our transfer function. And so the first one we're going to deal with, and we're going to talk about this one in the remainder of this lecture, is the constant gain k. It's a simple one to deal with, but that's a good place to start. Okay, so a constant gain. We can actually have a transfer function that is just a constant gain. It would look like h of s equals k. Now that's not very exciting, but that's not the point here. We just want to look at what happens when we have a constant gain as our transfer function. The first thing you notice is it is not frequency dependent. Okay, so not frequency dependent. All right, so that means it doesn't change with frequency. Um, so that should make it fairly easy to draw. And it turns out that it does. So if we want to, by the way, before I dig into that, k can be positive or negative. It can be any real number. So if we do want to look at it in terms of a magnitude and phase, then we can do that. So if k is greater than 0, then we can actually write it as just k at an angle of 0 degrees. And hopefully that makes sense. If k is less than 0, k is less than 0, then we're going to write it as the magnitude of k with an angle of minus 180 degrees. Now we could use plus 180, but most of the time when you see this in discussions, it'll be minus 180, although there's nothing wrong with using either one. Really, it's whatever might be advantageous to you. Okay, so the next thing we need to consider is we're going to talk about how to manipulate the gain. And really we want to make sure that we always write the gain itself is going to be in dB. So we're going to use 20 times the log base 10 of the absolute value of k. So that's always going to give us a positive number. And so that's what we'll put on our gain and our gain chart, our gain plot. So to draw our graph, we're going to look at our magnitude plot. So we'll just draw a little here. Now remember, when we do a Bode plot, we're going to plot the magnitude in dB. So we're going to say this is our magnitude in dB. So this would be, we'll call this our gain is 20 times the log base 10 of k. So we're just going to call that G. So I'm going to say that that's G, and that's in dB. And we're just going to have a constant value for that. So we'll just put a straight line out there. That's all there is to it. It's really not any more difficult than that. Okay, for the phase, we're going to go ahead and just draw a similar axis here that we're going to kind of scrunch it down here, but that's because this one's not that complicated. And again, remember, in both cases, we'll label a frequency axis usually as an omega, but it's actually going to be logarithmic, and it'll be the same for each case here. So that means what that would be is our frequency here would be, for example, 0.1 radians per second, 1, 10, 100, 1,000. Pretend those are all uniformly spaced. So that's our logarithmically spaced frequency points. Okay, same thing for magnitude and phase. So this is going to be the angle down here, and it's either going to be 0 if our gain was a positive number, or it will be at negative 180 if our gain was a negative number. But again, it will just be constant. And that's really all there is to drawing the frequency response of a constant gain transfer function. So this actually wraps up this first portion of our discussion. We will follow on with additional lectures to cover the other 6 types, and then we will look at some examples. I will remind you, if you haven't taken a look yet at the write-up that goes along with these, I strongly encourage you to do that, because I'm only hitting the highlights of some of that discussion to set the stage for what we're doing here. So anyway, thank you for your time. I hope you have a good day.